Hi students, in this video we're going to cover limit definitions of the derivative. To the right we have an animation that shows a red point quickly approaching a black point. Right now, as the red point approaches the black point, we have a secant line. Remember, a secant line is going to intersect the curve at least twice, and as this secant line as the red dot gets closer and closer to the black dot, instead of having a secant line, when the dot turns green, we end up with a tangent line. So remember the secant line, the slope of that line represents the average rate of change between 2 points. And as that red dot gets closer and closer to the black dot, the slope of that secant line when the dot turns green is going to be the slope of the tangent line. The instantaneous rate of change is the slope of the tangent line. In calculus, we call this the derivative of a function evaluated at a point. In this case, if the black point is this a f of a value, and then the red point is this a plus h, f of a plus h point, then h is just a very small difference between the fixed point and this point that is moving. It's just a very tiny difference. And so if we use our average rate of change formula, we end up with f of a plus h minus f of a divided by a plus h minus a. So because h is getting closer and closer to 0, this is going to be a good candidate for the concept of a limit that we discussed in Unit 1. And so as h gets closer and closer to 0, then we can manipulate this formula so we just end up with this part with no a in our denominator. And what we have here is the slope of the tangent line at the point AF of A. And again, that's going to represent the instantaneous rate of change at that point. So for example, one, we're going to write the equation of the tangent line for x equals 2 if we have this given f of x function. So we're going to always keep good notation for this. So we're going to have the limit as h approaches 0 of, so we're going to have negative 2 plus h. You know what, actually, let's do some side calculations so we don't have to do all of the work in one step. We're going to have f of 2 plus h minus f of 2 and just divided by h. I would recommend that we do these calculations of f of 2 plus h and f of 2 somewhere else. So f of 2 plus h is going to be negative 2 plus h squared plus 3 times 2 plus h minus 5. That should be a pretty routine step to show that we get 4 plus 4h plus h squared, and then plus 6 plus 3h minus 5. And if we further simplify this, we're going to get negative h squared. Let's see, we get negative 4 plus 6, which is 2, minus 5, which is 1. I'm sorry, negative 4 plus 6, which is 2, and then minus 5, which is negative 3. And then negative 4h plus h is going to give us negative h. So negative h minus 3. And then f of 2 is going to be negative 4 squared. Negative 2 squared plus 3 times 2 minus 5. I believe that is negative 3. So when we rewrite this limit with those values replaced, we're going to have the limit as h approaches 0 of negative h squared minus h minus 3 minus negative 3. Remember, this part is the f of 2 plus h, and the minus negative 3 is us subtracting f of 2. We divide by h. What should happen if you've done this process correctly is that anything that does not have an h disappears or it cancels out. So we get the limit as h approaches 0 of negative h squared minus h, because negative 3 plus 3 is 0, divided by h. Then we get the limit as h approaches 0. They all have an h in common, so we can divide out an h, and we get just negative h minus 1. And what we learned in the first unit is that substituting in is the easiest way to evaluate a limit, as long as you do not divide by 0. And since we are no longer concerned with dividing by 0, we can substitute in 0 for h, and we get negative 1. What this limit has told us is that the derivative evaluated at 2 is equal to negative 1. This value is the slope of the tangent line at that point. We already know that the point 2, negative 3 is on the curve. And so to write the equation of the tangent line, we're going to use the point slope formula. So that's going to be y minus negative 3 equals negative 1 times x minus 2. So y plus 3 is equal to negative x plus 2. And so y is going to equal negative x minus 1. What you should check is the point 2, negative 3 should be on both the tangent line and the original function. So if we substitute in 2 for the tangent line, we're going to get y equals negative 2 minus 1, which is negative 3. So because the point is on our curve and our tangent line, we believe our process is correct. So for you, you do this guided practice, pause it, and come back and see if you get the same result that I get. A hint here is use Pascal's triangle, or just multiply out 1 plus negative 1 plus h squared times negative 1 plus h, however you get there. All right, so if you're rejoining me, what we're calculating is f prime of negative 1. So we know that f prime, the derivative evaluated at negative 1, is the limit as h approaches 0 of negative 1 plus h cubed minus negative 1 cubed, all divided by h. And from Pascal's triangle, you should remember that we can actually like draw this off to the side. So you get 1, 1, 2, 1, 1, 3, 3, 1. And so this row is for x cubed, or a cubic, a binomial cubed. So what we're going to get is negative 1 cubed plus 3 times negative 1 squared times h plus 3 times negative 1 to the first power times h squared plus 1 times h cubed. The powers always add up to 3. If you just multiplied it out, it's not a big deal. So what we're going to get is the limit as h approaches 0 of negative 1 plus 3h minus 3h squared plus h cubed. And then if you substitute in negative 1, you're going to get minus negative 1, and all divided by h. Now again, what should happen is that anything without an h should cancel. So we get the limit as h approaches 0 of 3h minus 3h squared plus h cubed, all divided by h. So let's see, negative 1. So we get 3h minus 3h squared plus h cubed. Exactly. And then since everything has an h in common, we can divide out an h. We get the limit as h approaches 0 of 3 minus 3h plus h squared. And again, the easiest way to evaluate a limit is through direct substitution. By doing that, we're going to get 3, because 3 minus 0 plus 0 squared is 3. So the slope of the tangent line is 3. So f prime of negative 1 is equal to 3. And we know the point -1 is on the graph. So y minus -1 is equal to 3 times x minus -1. That's going to give us y plus 1 equals 3x plus 3. And y is going to equal 3x plus 2. So again, if you substitute in -1, in this case, we should get -1, and 3 times -1 plus 2 is -1. So if we have a function that can calculate the slope at a particular value, it's not a stretch to know that we can have a function that gives us the slope at a slope function for any possible value of x. And again, we call this function the derivative. It has this notation that the most common notation that we're going to use is f prime of x. So f prime of x. It's also called the first derivative. All of these notations are equivalent to the first derivative. You have d over dx of f of x. That is equal to f prime of x. Sometimes we'll have the equation written in terms of y, and what we get is called y prime. And sometimes we'll see the derivative expressed as two rates of change divided by each other, and that's going to be dy over dx. However we get it, the derivative function can be calculated as f prime of x is the same limit. So all we really did was, instead of having a fixed point a, we have an arbitrary point x, and we still get this limit definition. The limit as h approaches 0 of x plus h minus f of x divided by h. So almost the same thing, just no fixed value. So we're going to use this limit definition to write the equation of the tangent line at x equals 3. So we're going to first find the derivative function and then substitute in 3. We're doing this with a rational function out of the gates. So let's see. So what we know is that the derivative function should equal, so f prime of x, or the first derivative, is equal to the limit as h approaches 0 of 1 over x plus h minus 1 over x, all divided by h. And if we simplify this, we're going to get a common denominator in our numerator. So we're going to get the limit as h approaches 0. So we're going to multiply the left fraction by x in the numerator. So x times x plus h. So we still have that 1 over x plus h, really. And then we're going to have minus x plus h divided by x times x plus h. And all of that is divided by h. So all we've done is get a common denominator of x times x plus h. And if we keep going, we're going to get the limit as h approaches 0. So we're going to have x minus h. So negative h over x times x plus h divided by h. And remember, we've done this in class. If you have a fraction divided by a single denominator, multiply the two denominators. So we're going to get the limit as h approaches 0 of negative h divided by x, we'll say h times x plus h. And so then we're going to get the limit as h approaches 0. So negative h and h are going to just give us a -1. So -1 divided by x times x plus h. And now, excuse me, we can evaluate this limit without dividing by 0. And that's going to give us -1 divided by x times x plus 0, which is really just -1 divided by x squared. So we know our derivative function is equal to -1 divided by x squared. And we want to write the equation of the tangent line at x equals 3. So then f prime evaluated at 3 is negative 1 divided by 3 squared, which is negative 1/9. And so if we're going to write the equation of the tangent line, we also need the point that is on the line. And so we know f of 3 is 1/3. So y minus 1/3 is equal to negative 1/9 times x minus 3. And so that's going to be y equals negative 1/9 x. And that's going to be 3 times, excuse me, 3 times negative 1/9. Negative 3 times negative 1/9 is positive 3/9, which is positive 1/3. And then we're going to add another third. So we're going to get plus 2/3. Plus 2/3. So again, if you substitute in 3, you should get 1/3. 3 times negative 1/9 is going to be negative 1/3 plus 2/3 is 1/3. So this is how we know we've written our equation correctly. So again, we did the limit definition, did a bunch of algebra to cancel, and we end up with a derivative function instead of a slope value. So I want you to do this same process for the square root of x plus 1. My hint to you is you can multiply by the conjugate to make the calculation simpler. All right, so if you're coming back from the guided practice, we should get f prime of x is the limit as h approaches 0 of the square root of x plus h plus 1 minus the square root of x plus 1 divided by h. And so we are going to multiply by the conjugate. This is going to give us the limit as h approaches 0 of the square root of x plus h plus 1 minus the square root of x plus 1 times the square root of x plus h plus 1 plus the square root of x plus 1 divided by the square root of x plus h plus 1 plus the square root of x plus 1, and we still have that h in our denominator. So this looks very complicated, but I assure you that it's not. So in the numerator, we have a difference of perfect squares. Remember, a squared minus b squared is equal to a plus b times a minus b. And what we have is the right side of this expression. We have the a plus b times a minus b. So all we're going to get is, I'm sorry, keep your limit. So all we're going to get is the limit as h approaches 0 of, excuse me, x plus h plus 1 minus x plus 1 in the numerator. In our denominator, we're going to get h times the square root of x plus h plus 1 plus the square root of x plus 1. And again, what should happen is if you've done this properly in the numerator, all that should remain is terms without an h. So we're going to get the limit as h approaches 0. So this is going to really give you a negative x minus 1, and that's going to cancel with the x and the 1. So we get h divided by h times the square root of x plus h plus 1 plus the square root of x plus 1. And again, the h's cancel. And so now we can substitute in 0 without dividing by 0. And so we're going to get 1 over the square root of x plus 1 plus the square root of x plus 1, or 2 square root, 2 square root x plus 1. So our derivative function is f prime of x is 1 divided by 2 square root x plus 1. If you didn't get this by yourself, it's perfectly fine. Watch my process. We'll do tons of practice in class. Not a big deal. right, so we're going to say our derivative is this to clean up some space. So now we want the equation of the tangent line when x equals 1, so we have to calculate f prime of 1. So f prime of 1 is going to be 1 over 2 square root 2. We're just going to leave that as is. And then if we're going to write the equation of the tangent line, we also need to know what f of 1 is. So f of 1 is just going to be the square root of 2. So the equation of our tangent line is y minus the square root of 2 is equal to 1 over 2 square root 2 times x minus 1. So we're going to get y equals x over 2 square root 2 minus 1 over 2 square root 2 plus the square root of 2. And you know what? That's actually good enough. We don't actually want to simplify farther or further. All right, so that concludes our video on limit definition of the derivative. First part of the video, we covered how to find the slope of the tangent line at a specific point. The last two examples, we covered finding the derivative function or the slope function for a function in general. If you have questions, please talk to me in class. Keep practicing.